Welcome to Maths with EJD. We're currently talking about non-linear programming, non-linear programming. And so far, we've seen how to solve non-linear programs with the penalty method, where we have a penalty parameter, which helps to penalize the system when there's a violation. And then we have the barrier method, which ensures that the search does not go out of the feasible region. And currently, we are looking at the Karush-Kuhn-Tucker conditions, which is a generalization of the Lagrange multiplier. So in the previous video, we've looked at the feasibility of the Karush-Kuhn-Tucker conditions. After now, we'll be looking at the evolutionary algorithms for solving nonlinear programs. Evolutionary algorithms like simulated annealing, tabu search, genetic algorithm, and so on and so forth. Yeah. So, like I said, we have seen penalty method, barrier method, and now we are on Karush-Kuhn-Tucker conditions. So, um, I think I'll just state the conditions again. I did that in the previous video already. So let's remind ourselves of the Karush-Kuhn-Tucker conditions. Okay. So the basic statement is that if X star is an optimal point, if X star is an optimal point, okay, there exists, there exists Lagrange, there exists Lagrange multipliers, lambda I. So these lambda i's are for inequality constraints, they are for inequalities, and mu j's for equalities, mu j's for equalities, such that we now have four conditions: stationarity, primal feasibility, dual feasibility, and complementary slackness, such that one, we have stationarity. And by stationarity, we mean that the gradient of the objective function evaluated at the optimal point x star plus the summation over I of all the Lagrange multipliers multiplied by the gradient of the inequality constraint evaluated at x star plus the summation over j, over all j's, right, of mu j's, right, multiplied by the gradient. That's the derivative of the hj's of x, of hj's evaluated at x star. All of this is equal to 0. So that is the stationarity condition. And then we have the next one, which is the primal feasibility. Primal feasibility. Okay. So the primal feasibility simply tells us that the inequality constraints evaluated at x star, which is the optimal point, is actually less than or equal to 0. And the equality constraints evaluated at x star is always 0. That is about the primal feasibility. And then we go to the dual feasibility. Under linear programming, we talked a lot about primals and duals. So we can transform a maximization primal into a minimization dual, or a minimization primal into a maximization dual. So we have primal feasibility and then we have dual feasibility. So for the dual feasibility, we are simply saying that all the lambda i's are always greater than or equal to 0. That's all the Lagrange multipliers, and that happens for every Lagrange multiplier, for every I. Okay. So that is simply the dual feasibility. And lastly, we have the complementary slackness. That's the fourth condition, which is a complementary slackness, complementary slackness. So complementary slackness simply tells us that lambda I multiplied by the inequality constraint evaluated at the optimal point is always equal to 0 for every I, for every situation possible, for every I. So again, we see that this ensures, so if lambda I gi x star is equal to 0, that means that either of them or both of them are 0. Okay, so this ensures that either the constraint, either the constraint is active, meaning that gi of x star is equal to 0, or the multiplier is 0. That is, lambda I is equal to 0. That's what complementary slackness talks about. Now, having said that, right, since we are looking at KKT conditions with infeasibility, what we are then going to do is this. Okay, yeah, I just want to switch over to say sport for choice. Okay, this now and this. Okay, so let's talk about the fact that let's talk about KKT conditions. KKT conditions with infeasibility. So these conditions are not always feasible with infeasibility. So we need to understand that sometimes the KKT conditions actually fail due to infeasibility. So the conditions are not met. Meaning, and if the conditions are not met, we cannot get an optimal point, right? Meaning no solution, no solution satisfies all constraints. Okay, so let's take an example of this kind of situation. Let's add something, say, maybe something far away from this. Okay, let's go this. Now, let's take an example of this kind of thing. Example of quadratic programming within feasibility. Quadratic programming with infeasibility. Okay, so we have a question here to minimize f of x1 comma x2, which is equal to same problem, x1, same objective function like before, like the previous video, x1 squared plus x2 squared, but then it's subject to another constraint, subject to x1 plus x2 minus 1 less than or equal to 0, which is an inequality constraint. So in dealing with this now, we have the first step, which is to define the Lagrangian. Define the Lagrangian. In this case, we have an inequality constraint. So we are going to be talking about lambda. So we have L of x1, x2, lambda being an inequality constraint. If it was an inequality constraint, we would use mu. So this is equal to x1 squared plus x2 squared plus lambda into the constraint, which is x1 plus x2 minus 1, x1 plus x2 minus 1. That is the Lagrangian right there. And then we move on to the next one, step 2. Step 2. So for step 2, we compute stationarity conditions. Compute stationarity conditions. So this would mean us trying to, this would mean we have to check the feasibility. We have to differentiate, right? We have to find the derivatives. So first of all, we need partial L, partial x1. That means for this function, we differentiate with respect to x. So x1 squared gives us 2x1. Then another x1 squared is around here. So that's lambda x1. So we have plus lambda, and we equate that to 0. And then we're looking for lambda. So here we have 2x1 equals minus lambda. Okay. That means that x1 alone is minus 1 over 2 lambda. So we have this. Then, of course, we can also go for the next one, partial L, partial x2. Now, if you look at the way that is right, so we have x2 squared, which will give us 2x2 when we differentiate. So we have 2x2. And the next x2 is here. So that's lambda and x2. So when you differentiate x2, you also get lambda. So we have plus lambda again equals 0. And then that means that 2x2 is equal to minus lambda. And then x2 also is minus 1 over 2 lambda. So we have that settled. So the next thing we want to do is to solve for x1 and x2 in terms of, okay, we have got x1 and x2 in terms of lambda, right? Um, so we compute stationarity. So I've done two steps here: compute stationarity and solve for x1 and x2. We've done that together here. So for the next step now, which is step, that should be my step 3 now. So we have step 3. So for step 3, we want to check primal feasibility. So check primal feasibility. So that means that, so you remember primal feasibility talks about the constraints, right? So if you put the values of X you have got into the constraint, what do you get? So imagine the constraint. Okay, we can say the constraint, which is x1 plus x2 minus 1. Okay, so using this, right? The constraint itself is less than or equal to 0. So we know x1 is minus lambda over 2, or I mean, just like I said it should be minus 1 over 2 lambda, right? If you like, plus minus 1 over 2 lambda again, minus 1. So if you try to solve this, this is lambda minus lambda over 2 minus lambda over 2 minus 1 over 1. Okay. So this is LCM is 2. So we have minus lambda minus 2. And then that is equal to, okay, I think it's better to just use the whole expression. So it means we are going to get something out of that. Okay. So this is less than or equal to 0, as we have up there already. So this is minus lambda over 2 minus lambda over 2 minus 1 over 1 is less than 0 over less than or equal to 0. LCM is 2. So we have minus lambda minus 2 less than or equal to 0. So we can multiply through by 2, and we have minus lambda minus 2 is less than or equal to 0. Okay, if you multiply through by 2. So this is minus 2 lambda minus 2 is less than or equal to 0. So that means that minus 2 lambda is less than or equal to 2. That's if you transfer this 2 to this other side. And then we can divide through by minus 2. So minus 2 lambda divided by minus 2. Now, when you divide by a negative value, right, the sign has to change. So this becomes greater than or equal to 2 over minus 2, so that this cancels out, and lambda is greater than or equal to minus 1. So lambda has to be greater than or equal to minus 1. Okay, that's one thing we get from here. We have lambda to be greater than or equal to -1. That is established. And then we go for the next step. That's my step 4. Step 4. So we want to solve for lambda using complementary slackness. Complementary slackness. So like we know, complementary slackness talks about lambda I gi less to be equal to 0. That's what complementary slackness is about. It tells us that lambda I gi x star is equal to 0. Okay, we know our x's already, but somehow we've got lambda to be greater than or equal to -1, first of all. So here we can say that if x1 plus x2 minus 1 is less than 0, of course. So if this is, this is the constraint and it's supposed to be less than or equal to 0. So if x1 plus x2 minus 1 is less than 0, then lambda will be equal to 0. Okay. Then lambda will be equal to 0. Here we know lambda is greater than or equal to -1. So, but if this is less than 0, then lambda is equal to 0. But this contradicts, this contradicts our equation. This contradicts our equation. Thus, the constraint is active. Thus, the constraint is active, meaning that we can say that x1 plus x2 minus 1 is equal to 0. And what that simply means is that now we already know lambda x1 and x2, they are both minus half lambda k plus minus half lambda minus 1 equals 0. Okay. Now, already here we have ruled out the fact that lambda is equal to 0 because that's what complementary slackness tells us, that, you have lambda I, say you have lambda I gi of x star is equal to 0. That means either this is 0 or this is 0. But from what you have seen, right, lambda is greater than or equal to -1. So, but looking at the condition of the constraint now, if the constraint is less than 0, that means that, look at it here now. If the constraint was less than 0, that means that lambda would be greater than or equal to, that means lambda would be greater than -1. Okay, it will be greater than -1. And so that means it's possible that lambda is 0. So, but actually this contradicts our equation. So we can say then that the constraint is active, which means that x1 plus x2 is -1. So we can solve this now. We have minus lambda. Okay, so minus lambda over 2 minus lambda over 2 minus 1 is equal to 0. We can multiply 3 by 2 or take LCM, but I think it's easier to multiply 3 by 2. So we have minus lambda minus 2 equals 0. So that means minus 2 lambda minus 2 is 0. That means that minus 2 lambda is equal to 2. So lambda is equal to 2 over minus 2. Then lambda is equal to -1. So lambda is -1. Now, since lambda is -1, we can then check. But we can check dual feasibility. Check dual feasibility. That's step 5. Check dual feasibility. So for dual feasibility, we know that all the lambdas should be greater than or equal to 0, right? If you remember the condition for dual feasibility, lambda I should be greater than or equal to 0. But here we have lambda to be equal to -1. And that is like that's a contradiction for sure. So we can say the KKT condition requires lambda to be greater than or equal to 0, But we found we found lambda to be equal to -1, which is not feasible, which is not feasible. Okay. Then we can conclude on that and say that in conclusion, right, we can have that since the dual feasibility, since the dual feasibility condition is violated. In fact, I'm sure we didn't have to come this far to even decide, right? We already see here that lambda is either at the worst lambda is that it is equal to -1. And that already violates that already violates the fact that lambda should be greater than or equal to 0, right? So so since the dual feasibility condition is violated, then no feasible solution exists. So the problem is infeasible, meaning no x1, meaning no x1, x2 can satisfy both the optimization objective, both the optimization objective and the constraints. Okay. So with that done, can we look at some practice? Okay, so question 1, solve the following problem using KKT conditions and determine if a feasible solution exists. If a feasible solution exists. So the question is to minimize f of x1, x2 equals x1 squared plus x2 squared, subject to x1 plus x2 less than or equal to -1. Okay, so I think this is a case of infeasible linear constraint. Then we go for question 2. We can also have conflicting constraints like this. I mean, we saw things like this under um graphical solution, linear programming, basically. So we have conflicting constraints. So we can't even progress. So determine whether a feasible solution exists. A feasible solution exists. So like I said, it's a case of conflicting constraints where you minimize f of x1 comma x2, which is equal to x1 squared plus x2 squared, subject to x1 plus x2 less than or equal to 1. And at the same time, x1 plus x2 is greater than or equal to 3. So you can see that the constraints are already conflicting. So that's already going to be a problem. Okay. Then we go for the third example, question 3, where we have violating dual feasibility, just like the example we solved up there. So the following, check whether the following problem has a feasible solution, So the question is to minimize f of x1 comma x2 equals x1 squared plus x2 squared minus 2x1 minus 4x2, subject subject to x1 plus x2 minus 5 less than or equal to 0. And then we have 2x1 plus 3x2 minus 15 is greater than or equal to 0. So this is a case of violating dual feasibility. So these practice problems, of course, will help you solidify your understanding of how the KKT conditions apply to feasible and infeasible cases. All right, so that's how that goes. And of course, one take away from this lesson is that if any condition, especially dual feasibility, is violated, I think that is worthy of note, right? Um, and I think that's what we saw from the example we took, that if if any condition, if any condition, especially dual feasibility. And dual feasibility is where the Lagrange multiplier should be greater than or equal to 0. Especially dual feasibility is violated. The problem is infeasible. Problem is infeasible, meaning no valid solution exists. No valid solution exists. So that is the summary of this situation now. Okay, so I mean, let me see your practice, the answers to your practice questions. Let me see them in in the comment section, either on Facebook or on YouTube. So there's no need for Python code here because it's just following the conditions right there. Let me also know in the comment section if how helpful these videos are for you, and if you have a problem or a problem I can help you solve, or a topic I need to teach. If it's not too urgent, I might find time sometime in future to deal with those. Then if you have not subscribed already, you'll be missing out a lot. So don't be part of that. So be careful to subscribe and hit the notification bell so you can always get alerted each time a new video is released. For those who have subscribed, thank you so much. And of course, you want to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Watch out for the evolutionary algorithms, like simulated annealing, tabu search, genetic algorithms, uh, um swarm optimization or something like SPO, or PSO rather, particle swarm optimization. Yeah, and then there is another one that I'm not remembering right now, but we're going to deal with all of that, as we get on to that side, to talking about evolutionary algorithms for nonlinear programming. Till I come your way again, keep doing maths right. Bye.